Our position on the globe often puts us in winter's crosshairs as jet streams and colliding air masses clash over the Northeast in a breeding ground for big storms. I'm CBS 6 Chief Meteorologist Steve LaPointe. We have a long history of blockbusters here, punctuated by storms like this one in December 1969, when the third largest snowfall on record at Albany paralyzed the region, even disrupting construction of the Empire State Plaza. Snow-clogged streets for up to a month in Albany, with staggering cleanup costs in the millions. This was the second of two back-to-back storms separated only by 4 days, with the first one dropping a foot of snow on December 22nd, followed by over 2 feet from this one in what amounted to a 3-day onslaught ending on the 28th.
Well, since you've been manager here, John, have you ever seen anything like this at Albany County Airport?
No, this is the second biggest storm in the history of the Weather Bureau, as a matter of fact. It's the second storm since 1888. I don't remember that one, but I'll sure remember this one.
Of the top 5 snowstorms on record at Albany, which includes the 1969 storm, none comes close to the widespread, staggering 3 to 5 foot accumulations in the March blizzard of 1888. Albany's all-time single storm snow record was set in this storm with an astounding 46.7-inch accumulation. 58 inches piled up at Saratoga Springs. The much more recent blizzard of '93 was a distant second locally in terms of snowfall with a little over 2 feet, but does rank as one of the all-time greatest storms on record nationally due to its scope of coverage. The National Weather Service defines a blizzard as a severe snowstorm characterized by strong sustained winds or frequent gusts to 35 miles per hour or higher and visibility of 1/4 mile or less for a duration of at least 3 consecutive hours. To date, the March blizzard of '93 remains one of the largest and most powerful mid-latitude cyclones ever observed, affecting 26 states, including 40% of the U.S. population from the Gulf Coast, deep south Appalachians to Maine. It was an epic storm here, one of the few true blizzards to have slammed our area, and one which left a lasting impression on me as I covered it very early in my career at CBS 6. Total storm accumulations of 20 to 30 inches, much of the capital region, 28 to 40 now possible in the Catskills and the Berkshires, southern Vermont, and the Adirondacks off to the north. Blizzards on average are a once-in-a-decade type storm here and are an extreme example of a nor'easter, a more typical winter storm which comes in different sizes, configurations, and intensities. They feed on large temperature contrasts in the atmosphere generated by the collision of Arctic air from the north and the relatively warm air over the nearby Atlantic Ocean. Strong jet stream winds help to intensify them, causing some to develop rapidly, pressures falling so fast that we call them bombs. A cold wind here blows from the north-northeast, which is why they're called nor'easters, and depending on their track and temperature can produce epic snow, ice, or rain, with the ultimate outcome often difficult to forecast.
The greatest challenge in any nor'easter we have is that temperature profile. Huge factor in our forecasting capabilities is trying to figure out where the rain snow line is going to be and who will get impacted when it gets cold enough.
If the storm track is 50 miles difference, if it's 50 miles too far west, we end up seeing a snow and rain mix or mix of slop, as we like to say. If it's 50 miles too far east, we see very little snow, sometimes just cloudy skies. People need to realize that, again, a subtle shift in storm track can mean a big difference in snowfall totals. And I think one of the biggest things that most people don't realize is that the weather can change dramatically in a very short distance. The gradient between no snow and a lot of snow is often very narrow.
And it's often so narrow because nor'easters produce their heaviest snow through smaller scale banding features like the ones shown in these radar images from the Valentine's Day 2007 storm. The areas of red showing where incredible snowfall rates of 4 to 6 inches per hour were occurring, resulting in a huge zone of 20 to 30 inch accumulations, making this one of the all-time greatest nor'easters on record locally. Similarly, on Christmas Day 2002, an equally powerful but compact nor'easter with intense banding dropped 21 inches of snow on Albany in an incredibly short 10 hours. And we have a very narrow band extending from just to the west of Glens Falls, through northwest Saratoga County, now through much of Fulton County, western Montgomery County, western Schoharie, eastern Otsego, and Delaware County. In this zone, the snow, as reported by our WeatherNet 6 weather watchers, is coming down at about 4 inches per hour, so exceptionally heavy snows in here.
These bands and some of them are very hard to forecast. The bigger ones are the ones that are usually, you can kind of identify them at the little bandlets, so we'll call them bandlets. They're the ones you got to watch out.
And once in a while, something dramatic like this will happen right in the middle of the storm.
Suffice to say, you need a very powerful storm with a lot of turbulence, and you need a mixture of snow, sleet, and rain in the storm. And then that turbulence and the mixing of the ice and the water create static charges, which can give off lightning.
How much snow that piles up at your house from a storm is only partially governed by the storm itself and how it tracks. We've learned through local studies that it's our unique terrain which comes into play, having a huge impact on why one area gets just a few inches with another a few feet. And the effects of terrain were most dramatically illustrated in a massive slow-moving storm in December 1992, a nor'easter which flooded the streets and subways of New York City with storm surge. It produced hurricane-force winds from Long Island to Boston, and it dumped up to 4 feet of snow on the Berkshires and 3 feet on the Catskills. But in the capital region, only a mere 6 inches fell after periods of rain and sleet. Here's National Weather Service meteorologist Hugh Johnson with insight about that storm.
We had easterly winds at all levels of the atmosphere, at least through the first 10,000 feet, very strong 50-knot winds or better. And because of that, we had this downslope going on. And actually, the argument was a lot of the moisture literally blew over the Hudson Valley. It didn't just downslope, it blew literally over the Hudson Valley into the areas to our west. And downslope, the moisture, because it's being forced down at a greater rate than normal, is actually being dried out. But when it gets slammed up on the other side of the terrain, then it's being enhanced and lifted upward, and it's producing heavier amounts of snow, heavier banding of snow. And we saw the Berkshires got up to 4 feet of snow in some spots.
Another unique terrain effect specific to only our area is the Mohawk-Hudson convergence, which occurs in cases when a departing storm leaves a northerly wind in the Hudson Valley, which then collides with a westerly or northwesterly wind in the Mohawk Valley, with that convergence taking place right over the capital region. The result can prolong snowfall, leading to several additional inches, and it's tough sometimes to see it coming with only an hour or two of lead time.
It's pretty difficult because it doesn't always happen. And the reason why it doesn't always happen is because a couple things have to happen. There has to be low-level moisture in place. There has to be a storm that's not moving too quickly. Sometimes you get like hybrid situations where actually you do get a little bit of a northwesterly flow and it can actually slam against the tectonics. And then you get enhancement, you get upslope and Mohawk going at the same time. So Rensselaer County really can get the brunt of it sometimes.
And it's not always snow that we deal with. Sometimes it's a wintry mix or worse, an all-out ice storm. The National Weather Service issues an ice storm warning when ice accumulations of 1/2 inch or greater are expected, which is the threshold for when branches start to break and fall. Ice accumulations of over 3/4 of an inch and damage to trees and power lines becomes exponentially worse. This was the case in early December 1964 when ice accumulations of 1.5 inches left Schenectady and the surrounding area looking like this, with miles of downed trees and power lines. The ice storm, regarded even today as the worst to hit the region, caused power outages lasting up to 2 weeks, schools shut down for a week, and $5 million locally in estimated damage. Fortunately, big ice storms like this one are fairly rare, but some icing typically does occur every season.
In most winters, we probably get a half dozen local areas of, pockets of freezing rain. I don't know about widespread across the entire area. Certainly the Mohawk Valley, the western Mohawk Valley, especially susceptible to ice, the Adirondacks, parts of the Hudson River Valley. But it can happen anywhere in our forecast area. But usually it's a localized area, maybe 1 or 2 counties. And the glaze is usually not enough to bring down trees, but it's enough to make driving hazardous.
The December 2008 ice storm was much more than just a light glaze. A narrow zone of damaging ice over 3/4 of an inch thick sliced across the capital region, leaving 250,000 without electricity, while the Mohawk Valley, Adirondacks, and Lake George, Saratoga regions instead got heavy snow and sleet. And determining where ice versus sleet and snow falls in a storm like that is a difficult forecast challenge.
There's usually a very narrow differential between the snow, sleet, and freezing rain. Where that line exactly sets up, I think in the 2008 storm we were expecting snow here locally in the Capital District. The snow actually fell in Amsterdam and it fell in Saratoga, but we ended up with mostly freezing rain here. I would probably say if freezing rain, a prolonged period of freezing rain or an ice storm warning is in effect and you're within 30 miles of the warning area, expect that there's a potential that you may see that ice storm as well, because again, a subtle shift of only 25 or 30 miles in the storm track or that rain snow line could mean the difference between snow and ice.
And to understand why the lines between snow, sleet, and freezing rain are so fine, we need to look at how the layers of cold and warm air at different levels of the atmosphere come into play to determine what type of precipitation falls to the ground. A warm atmosphere supports rain. A cold one, typically with temperatures below freezing from top down, supports snow. It gets trickier when sleet comes into play. For that, we need a warm layer, temperatures above 32, wedged between two deep layers of sub-freezing air. Snow falls into the warm layer, melts into the rain, but then has a sufficiently deep layer to refreeze into those ice pellets that make their way down to the ground. For freezing rain, this warm layer aloft is actually much, much deeper. So what happens here is snow falls into the warm layer, melts into rain, but the rain doesn't have enough time before reaching the ground to refreeze into those ice pellets. Instead, it freezes on surfaces, causing the icing and the glazing. And when freezing rain falls for prolonged periods of time, that's how we get an ice storm. So that's a bit of insight into the mechanisms behind winter storms in this area and how it's not just about the storm itself, but also the temperatures in the atmosphere at the time and how our local terrain ultimately comes into play to determine the unique outcome of each storm and how those outcomes can vary so dramatically from one part of our area to the next.